I'll be back for the final discussion.
Thank you, Cecilia. I think this is a wonderful starting point. And Carlos, do you want to share your screen and start your presentation? We keep the questions and the discussions at the end of the session. So please post your questions in the chat or Discord, and then we will pick this up. Okay, Carlos, you go ahead.
Yes, thank you very much, Mia, for organizing and also for accommodating all my agenda complications. I just want to share some perhaps more philosophical thoughts about the limits of artificial intelligence that we've been discussing with several colleagues in recent months. So just a bit of historical background, we could say that our species has had three major revolutions: agriculture, industrial, and information. And then we could also very generally say that the first one dealt mainly with the control of matter, the second with control of energy, and the third with control of information. And the fields that were advanced most in each were mechanics, thermodynamics, and computer science. And each of these had immense transformations in our societies. With agriculture, we went from being nomads to sedentary, so that allowed the emergence of cities, and that had many implications for social complexity and development of new technologies and ideas and so on. With the Industrial Revolution, of course, there were many more changes than the one I mentioned, but for example, the distances became shorter because we could travel much more, and electricity paved the way for the information technology. And we've had, thanks to computers, we are able to study intelligence or mind or whatever we want to call it, or cognition, because it's mainly about information processing. And it has also allowed us to study complexity because you need to process large amounts of information to consider interactions in a complex systems, and both of them have the roots in cybernetics. So another brief story about the limits of formal systems. Cantor was a German mathematician, late 19th century. He made several contributions, even when he was mocked and ridiculed by his teachers and colleagues. But basically, he solved many problems that were standing in mathematics. Let's say modern mathematics have their basis in Cantor's work. And he was ridiculous because he was actually the first one to define properly infinitesimals. But then by doing that, well, basically setting the base of set theory, and let's say we could say that mathematics are based on set theory. But then many paradoxes began showing up in different sets. And perhaps the most famous is Russell's paradox, where, let's say, you have the set that contains all respectable sets. And well, I won't go into that, but let's say there were, let's say, problems in the early 20th century in mathematics. So in the 1920s, David Hilbert, who was perhaps the most respected, famous, capable mathematician of the day, in Göttingen in Germany, he proposed a program to prove that mathematics were consistent, complete, and decidable. And his PhD student, John von Neumann, that we know from his later contributions to quantum mechanics and atomic bomb and computers and artificial life and I mean many other things that he contributed. He was working on this for his PhD and failed miserably. Well, not miserably, but Kurt Gödel actually proved in 1931 that not only mathematics but all formal systems based on axioms were not complete and not consistent. And von Neumann was the only one who understood that at first because he had been working on the problem, but then it spread, let's say, quickly, but many mathematicians did not accept. And then 5 years later, Alan Turing proposed the now called Turing machine precisely to attack the decidability problem posed by Hilbert. And he showed also that formal systems are not decidable. And later Greg Chaitin added even more wood into the fire, showing different limits of formal systems. So to summarize, what Gödel, Turing, and Chaitin have done is to show that mathematics is not perfect, or let's say we cannot be completely sure about formal systems. Still, in practice, we use them, and we have built computers using formal systems. But then the question is, okay, if we build artificial intelligence systems based on computers that are built with formal systems, are they subject to the same limits, and whether the limits of artificial intelligence are related to the limits of formal systems? And I mean, this is a question that we just began exploring. And I mean, I just list a couple of limits of AI, but there are many more, and we already mentioned them in the introduction. So we could just speak a bit about meaning, let's say semantics. This is related to the Chinese room problem, to the symbol grounding problem. I mean, much has been written about this, and also about artificial general intelligence, that computers or AI algorithms seem to be very good for specific tasks, but not for general tasks. And the question of why this is the case seems to me to be related to the limits of formal systems, because in order to have flexible machines that would be able to acquire new meanings or to adapt old meanings to new contexts, you would need to be able to do something equivalent to change your own axioms. And of course, we could devise a system where, let's say, you have like a bottom layer that you don't change, and then there's a higher layer, and then there are some flexible axioms there, and then you can have some sort of adaptivity. But of course, at the bottom layer, then you don't, you cannot change those axioms. But then we could say that also we somehow managed to acquire meaning and artificial, or not artificial, we exhibit general intelligence, and we cannot change physics. So in a sense, we also have a limit on the axioms that we cannot change. And these limits of formal systems are also related to those that we find in artificial life. So for example, there's this debate whether we can build open-ended evolution in artificial life systems, either software or hardware. And of course, there's the question of what do we mean by open-ended evolution? But this also applies to adaptation and learning, in the sense that in many cases, we do build adaptive systems, but then their adaptation is limited. And then how can we go beyond those limits? Seems to me it's also related to questions posed by Gödel and Turing. And also, when more generally we're studying complex systems, the open issue of strong emergence, that basically properties that not only arise from interactions of the components, but also have causal influence into the components. So this is also known as downward causation. There's a debate even whether downward causation exists or not. But it seems to me that, well, first of all, I'm in the camp believing that it does exist, just like individuals define social norms and then social norms define individuals. I see that as an example of downward causation. But we do lack the formal framework to describe downward causation and stronger emergence. So, and it seems to me it's precisely because of the limits of formal systems. So what can we do? We could try to, let's say, develop more sophisticated formalisms, but since it is proven that all formal systems have these limits, it seems that's not the way to go. And especially, I mean, we've been doing this for almost a century, and I mean, those limits are still there, and it seems they won't go away. And one promise could be that perhaps there's enough richness in the real world that is lacking in our models, and precisely embodied approaches and embedded approaches could overcome these limits. But then, of course, we would like to describe them, and it seems that our models, since they are in a way based on formal systems, then they're unable to capture that richness that we might or might not find in the real world. And perhaps also it's just not really a problem, because at the end, formal systems we can see as models, and then that's different from the model. So let's say reminding us not to confuse the map with the territory. So if we are just thinking about descriptions of phenomena, in this case of intelligence, and that descriptions have limits, then that doesn't mean that the real system has limits. And of course, we could, in theory, build real intelligent systems that also don't have those limits, but then we would be limited in their understanding. And just to conclude, I think that maybe these limits have also been demonized, in the sense that they see it as, we see them as something bad, but perhaps it's better to have these limits than not to have them. Because imagine if Hilbert's program had been a success, then okay, we would have certainty, we would have truth, we would have completeness, but then we wouldn't have creativity. Because at the end, in order to have creativity and ambiguity and flexibility, you need to be able to have meanings with polysemy, basically the same thing having different meanings, and then to change their meaning. So the richness that the limits of formal systems give us, it seems to be more valuable than the certainty we're trying to achieve by overcoming these limits. So perhaps we should better try to embrace the limits and see how far can we go without the certainty of saying, okay, our model is precisely defined, our robots will precisely do this, and if we allow them to be incomplete and inconsistent and undecidable, maybe we will be able to go beyond those limits. But of course, these open questions. So what I tried to put on the table to further discuss is that the limits of formal systems have relationships with the limits of artificial intelligence. And then the question would be, should we try to go beyond those limits by making better models, or accept those limits and work with them, let's say, use them more as a tool than as an obstacle? But of course, I basically posed many open questions and no answers. So I'm looking forward for this
Okay,
session.
thank you. Thank you very much,
Thank you.
Carlos. This was a wonderful presentation, and especially about the philosophical questions. It's not easy to discuss in openly, but I think you put it in a very nice way. So I understand you have to leave now, but please feel free to join later for discussions if you can.
Yeah, I can still stay for half an hour, but thank you very much.
Great.
Yeah.
Thank you very much, Carlos. And this was a wonderful presentation.